Everything that we have looked at so far has involved interpolating in one dimension. Often, however, in real applications, we're going to want to interpolate in more than one dimension. We'll have data, for example, defined on a plane, so we have an x and a y coordinate, and some kind of function value defined on a surface. And we may want to interpolate that function. So that is known as multi-dimensional interpolation. And today we're going to look at multi-dimensional interpolation on regularly gridded data. The simplest form of multidimensional interpolation, and I'm just going to give the example of 2D interpolation here, is known as bilinear interpolation. So let's have a quick look at how we do interpolation in one dimension. So in 1D, the linear Lagrange polynomial is written as this function here. You should all know that quite well by now. And this just represents a straight line. So if we have the data y1 at x1 and y2 at x2, we can use this straight line function here to interpolate to any other point x. We just plug in the value of x and we get the appropriate value of y. So we're using a straight line to interpolate between the points y1 and y2. We can do a similar thing in two-dimensional. And so what we're going to do is we're going to fit a surface to the function values f of x and y. And students often get a little bit confused when we move on to multidimensional interpolation because they're used to y being the function value that we're interpolating. But for everything in multiple dimensions, y is actually a coordinate, and the thing that we're trying to interpolate are the function values f. So x and y are our grid points, the function values are the function values at those grid points. So with bilinear interpolation looks a little bit like this. So if we have our x and y grid, and so this is the x-axis here, and that is the y-axis there. We have 4 points. At each of these points we have a function value. And what we're trying to do is we're trying to estimate what the function value is at some other point that's not one of our data points. So in other words, what is this value up here? So if you view that previous case from above, we have our 4 points, evaluated by coordinates x1, y1, x2, y1, x2, y2, and x1, y2, and at each of these points we have a function value. Those function values effectively, if you like, are coming out of the page toward you. And then we have some other point, x, y, that sits inside this rectangular domain, and we want to know what the value of the function is there, based on the function values at the corner points. Without going through the derivation, I'm just merely going to state that the function value there, according to the process of bilinear interpolation, is just given by this expression here. So let's have a quick look at what this is actually representing. So the function value at xy depends on the function values at the 4 corner points. That's what we expect. But there's a multiplying factor out the front of each one. So let's look at these multiplying factors. Let's consider, to begin with, the function value at x1, y1. So that's the function value at the bottom left-hand corner here. So what we're saying is the function value at this point here is a weight that's based on the 4 function values, and the weight for this point here is given by the area of this rectangle here divided by the area of the total rectangle. So let's have a quick look at this. So the area of this rectangle, the one on the top right there, is equal to, well, that's x2 and that's x, so that distance there is x2 minus x, and that's exactly what we see here. And the height of that rectangle is equal to y2 minus y, which is what we see here. And the total area of the rectangle is just x2 minus x1, that's the length of that bottom side, multiplied by y2 minus y1, which is the total height of the rectangle. And that's what we've got there. So the function value at x1, y1 has a contribution to the interpolation that's based on the area of the diagonally opposite rectangle divided by the total area of the whole rectangle. Now let's move to the point x1, y2. That's that point up there. What we're saying is the contribution of this point to the interpolated value is given by the area of the diagonally opposite rectangle, that's x2 minus x times y minus y1, divided by the total area of the rectangle. Likewise, for the point x2, y1, its contribution is that rectangle, that fractional area of that rectangle divided by the total one, and finally f of x2, y2 is equal to the fractional area of that rectangle divided by the total one. And so if we go and add this to this to this to that, and add those together, we will come up with the area of the rectangle. So together, these four coefficients add up to 1. And this basically is an area-weighted interpolation. That's what bilinear interpolation is. And you can do this in more than 2 dimensions. You can do it in 3 dimensions, 4 dimensions, as many as you like. Of course, these expressions, these multiplying factors out the front, tend to get a little bit trickier as we move into higher dimensions. But its basic idea is the same. So that's bilinear interpolation. It is absolutely the simplest kind. The function that you get from that interpolation is continuous across cell boundaries if you were to move from cell to cell. However, the derivatives of the interpolated function will not be continuous. And so sometimes, as we know, we may want to have continuous derivatives. So what I'm going to do now is describe a general approach for doing 2-dimensional interpolation on regularly gridded data. And by regularly gridded, I mean we have only one set of x values and one set of y values. And so all the data points lie on straight lines, either horizontal straight lines or vertical straight lines. And if we have a grid that goes from x1 to xm, in the x direction, from y1 to yn, in the vertical direction, in general, we're going to want to find the data value at some point xp, yp. And I'm going to give you a general approach for doing this. I'm not going to specify what kind of interpolation it is. The first thing we need to do is choose a direction. And I am going to choose the x direction here. I'm going to say we're going to start doing things in the x direction. Okay, so that's a vertical line that's at x is equal to xp. And we're going to choose a scheme. For example, you could choose a cubic spline, you could choose Lagrange polynomial, you could choose anything you like. And what we're going to do is we're going to interpolate our function values at a set of points. The x value will always be xp, but the y values, in turn, will be each of the different y values that we have on our grid. And we're going to do this for each of our y values. So schematically then, what we're going to do, we're going to start off for y is equal to y1, we're going to take those points that I've highlighted there in blue, we're going to take our chosen scheme, for example, cubic splines, and we're going to interpolate along that line there and calculate the function value at xp, y1. That's that point there. We're then going to move up to y2. We're going to take those data points and we'll interpolate at that point there. So that's f of xp, y2. Go up to the third point, interpolate at that point, then do all of the other points in sequence until we've interpolated a set of data points at x is equal to xp. Then, we have all of those data points then. We're going to use the same scheme. Well, in actual fact, you could use a different scheme if you wanted to, but it probably doesn't make sense. But use your spline scheme, for example, to now interpolate in the y direction, but using only the pink points. So we then fit a spline to these data points here and estimate the function value where we want it to be. And that's the simple way of doing multidimensional interpolation. Of course, the devil will be in the coding detail.